All right, this is our last section for chapter 4. Trees, also known as twees. In the previous sections, we had special types of paths. So 4.1 through 4.3 were related because they were all special types and paths. We don't have paths in this section. So that concept is gone. Also, we had algorithms, specifically the nearest neighbor method, in the previous section. And I don't want you to confuse it with a process in this section when we find what's going to ultimately be called a minimal spanning tree. So do not get them confused. And how would you pronounce the last sentence there? I guess you'd scream that. Oh. Okay. Start off with another term. I know it's like number 47. A subgraph of a graph includes some of the vertices of the original graph. So the original graph is on the left there, A, B, C, D. It's a complete graph. It doesn't have to be a complete graph. And all three of these in the yellow, red, and blue are subgraphs. In the first one, we have A going to B and C. That's it. The second one, we have a circuit, A, B, D, C, A. In the third one, we have the edge from B to C, and then vertex D is just chilling out there. Notice a subgraph need not be connected. There's no rule for that whatsoever. So as long as it includes some of the vertices and the edges of the original graph, you're fine. The only rule is you can't have an edge that doesn't end at a vertex. That's the only rule. So you can have a vertex just floating out there, but you just can't have an edge just floating in space. That makes no sense. It has to be connected to vertex. Okay. Now there is a new hierarchy going on in this section. So a subgraph is at the top, and then below that we have the concept of a tree. A tree is a graph that is connected and contains no circuits. So of those three boxes that we already saw before, one of those is a tree. Which one is connected and contains no circuits? I don't want to sing the Jeopardy song because I don't want to get sued. Anywho, notice the very first one is a tree. I did not mean to write in red there, but that's okay, because it's connected and contains no circuits. The next two are not trees because this one has a circuit. I put an extra I in there, so 2 dots for you. And how about the last one? The last one is disconnected. Remember, disconnected is a math term. Disconnected means you can't go from, there's no path that connects any two vertices, so there's no way to go from B to D, for example. So only the yellow box is considered to be a tree, a connected graph that contains no circuits. Now, if I ask you what's the definition of a tree, you're right, a connected graph that contains no circuits. Done. However, there are properties of a tree, and don't confuse a property with a definition. I'll get to that in a second. So a tree has all the following properties. There's only one path joining any two vertices. Every edge is a bridge. And a tree with n vertices has n minus 1 edges. So don't list one of these specifically and call it a tree. For instance, number 2 there, every edge is a bridge. If I said, what is a tree? And you said every edge is a bridge, well, that's not correct. Because, for instance, I could draw this guy is my graph. Well, every edge is a bridge, but is that connected? Nope. So saying just number 2 is not sufficient. So properties do not make a definition. So for instance, if you said the property has an amazing beard, well, that doesn't define me. I don't define myself by my beard. So that's just a property, not the definition. So please don't mix those two up. Okay. Now, for a given graph, there can be many trees. So the given graph is on the far left there, and in the purple and green boxes, we have examples of some trees. Just like a path, a tree need not be of a certain size. So in the purple one, notice I didn't even include vertex D whatsoever. What are you going to do? In the green one, I included all the vertices. The one in the green is going to have a special name pretty soon here if you include all the vertices of the original graph. But again, if I just had A to B, B to C, that's a tree because it's connected and contains no circuits. So at the top we have subgraph, and underneath that we have tree. So here's the next one. A tree that uses all the vertices of the original graph is called a spanning tree. Well, I kept the green one the same. I modified the purple one. So these are both spanning trees for the original graph. Notice in both, and also in the previous slide there, did I include the loop? Nope. Why didn't I include the loop? Because a loop is a circuit, and that's bad. Okay, very good. So spanning tree is a tree that uses all of the edges of the, all of the vertices of the original graph. Bink! When finding a spanning tree, never create an edge nor a vertex that does not appear in the original graph. So if I went back real quick, notice that vertex A does not directly connect to vertex D. So in my spanning trees, I cannot create an edge that connects A to D. That's typically the bigger error, making an edge that wasn't there. So with that, if you would, please watch Finding Spanning Trees.